Hi, welcome back. In this lecture, I would like to talk about an important quantum computing primitive called QFT, that stands for Quantum Fourier Transform. Before starting the lecture, I want to clarify some nomenclature and explain what is DFT, FFT, and what is the quantum counterpart of DFT, that is the QFT. So the DFT is the conventional discrete Fourier transform that allow us to extract frequency information from a conventional signal. So typically we have some signal, and when applying the DFT, we can extract information about the so-called spectrum. What are the frequency of this signal? So typically we might have a plot with some peak that represent the frequency present in the signal. The FFT is the fast Fourier transform and is a specific or a class of algorithms for implementing the DFT. The fast Fourier transform performs precisely the same transformation of the DFT, but is significantly faster in practice. So a naive implementation of DFT is big O of n square, where n is the input size. The FFT is significantly faster, so complexity of n log n. You might have heard the different FFT algorithm, for instance, Cooley-Tukey, Stockham, Peirce FFT. So these are both are DFT and FFT are classical implementation that allow us to extract frequency information from conventional signals. So the QFT stands for quantum Fourier transform, and it performs the same transformation as the DFT and FFT. However, it operates on signals that are encoded in quantum register. And typically, these signals are encoded in the phase of our quantum state. And this as opposed to conventional information that is stored in streams for DFT and FFT. The quantum Fourier transform is a quantum computing primitive that allows us to access hidden patterns and information stored in the QPU register, relative phase and magnitude. Somehow it's also similar to the amplitude amplification in the sense that allow us to extract information also from the phase that we cannot measure directly. Differently from the amplitude amplification primitive, the QFT primitive has its own way of manipulating phase. We see that it will perform a phase manipulation, but also there is a part about computing in superposition. The quantum Fourier transform is a super important component of a very famous algorithm. You might have heard about the Shor algorithms for a factorized integer number. So QFT is a critical component of the Shor algorithms. Also, we're going to use on the next quantum primitive called phase estimation. These slides is probably the most important slides of this lecture because it's giving you a very intuitive way to understand how QFT operates. On the top, we have our circular notation using a multi-qubit system. You have 16 states, and then you see that we have a signal that is encoded in the relative phase. You see there is a rotation of the relative phase of 45 degree for each of the state. We can see also as a sinusoidal kind of signal. Sorry for my bad drawing, but we see that the signal is encoded in basically two oscillation. So we encoded the signal in the relative phase of the quantum state. This is somehow similar to this sinusoidal, for which we have two oscillation, one here and one here. So in some sense, the frequency is is 2 in all the signal. So applying the QFT allow us to retrieve this frequency that is equal to 2. So a quantum register has a signal that has some frequency that is associated with it, and this is the top panel. If we try to read it, we won't be able to read this frequency that is encoded in the relative phase. And the reason for that is that the magnitude of the states is all the same. All the states have the same probability of be read. The information is hidden in the phase, but we can actually apply the QFT primitives and get this information out of this phase encoded signal. The QFT circuit is depicted on these slides. As usual, we have a first step that put all the states in superposition, and then it applies a rotation, and this is basically just to encode our signal in the relative phase. And then we have the quantum circuit that is going to extract the frequency out of this signal here. So this is 4 qubits, so we have 5 components. So we have first one you see here is a series of Hadamard gate, and we have a second block here, Hadamard gate and control rotation, a third block here and Hadamard gate, and then a final block with the 2 swaps. So let's look at different steps. The first step is the actual preparation. So we encode our signal using Hadamard gate. So all the probability of measuring each state is the same. So the magnitude is the same. And then we applied a ROT of 45, 90 degree and 180. That it will allow us to get the signal that we've seen in the previous slides. Then we apply the first block of the QFT, and what you see, the effect on the circular notation is basically downsampling by half. Right? So we are decimating by 1/2 the original signal. We repeat the second block, right? That is this one. So this is the circular notation of the quantum state after the first block of the QFT, and after the second block we further down sampling the signal, so by in this case 1/4 of the original signal. The third block has a very similar effect, that is cutting in half the quantum states, and then we have a Hadamard gate that is cut in half from 2 to 1. And then we have two swaps here that put in the correct frequency. So this is the last slides, and talk to you soon.